Okay, here we go, my friends. We're looking at our notes. Important concept, every operation has exactly one inverse operation. So we know that the inverse of addition is subtraction. Kids, that's the concept you use when you solve an equation like x plus 3 equals 7. What do? To undo the addition, you subtract 3, right? That's what inverses do, they undo. So what's the inverse for multiplication? Division. The inverse for cubing is cube rooting. And the inverse of exponentiation is logarithms. Okay? Logarithms. Just as we can write rational numbers in decimal form and fraction form, when you take 0.5 and write it as 1/2, it looks different, but have you changed it? No. So just so we can write numbers that way, we can write equations in exponent form or logarithm form. We can go back and forth and they mean exactly the same thing. So, the exponential form, b to the 8th equals c, is the equivalent of the logarithmic form, log base b of c equals a. Now, let's link this back to last year. When you had a problem that said the log base 3 of 9 is 2, did you talk about loop-de-looing last year? I can't, what vocabulary did Mrs. Coors use? Log rolling, loop-de-loo? Well, I'm going to say loop-de-loo. If she didn't say either one of those things, I don't know what she said, so I'm going to say loop-de-loo. Start right here, 3 to the 2nd equals 9. This equation and this equation are exactly the same equation. They say exactly the same thing in a different way. All right, so hang on to that thought. We're going to need it in a minute. If the base of a log expression is 10, this number is called the base. If the base is 10, it's called a common logarithm, and it's usually written without the base. So if it says, log x, that means log base 10, common logarithms. Similarly, if we see ln x, that means log base e, and these are called natural logarithms, okay? So ln is just a logarithm with a base of e. So everything we do with our LOGs, we can do with our LNs. It's just a different kind of logarithm. All right, so example 1. We are going to convert the following equations from exponential form to logarithmic form. Okay? So 3 squared equals 9. That will be log base what? 3. When we say 3 to the 2nd is 9, isn't 3 the base of the exponent? Isn't that our base number? That stays the base of the logarithm too. So log base 3 of 9 equals 2. Because 3 squared is 9. The value of the logarithm is the exponent. So 10 to the x equals y. That will be log base 10 of y equals x. R to the teeth equals w. Log base r of w equals t. Perfect. Beautiful. Y equals e to the 3x.
Log e y.
This will be log base e
To the y, or
of
y.
y equals 3x. And of course, if you wanted to, instead of saying log base e, we could say ln y equals 3x. These are the same thing. Now, no mathematician is gonna write log base e, they're gonna write ln, because that's the symbol on our calculator. But these are exactly the same thing. Okay, now, can you go the other way? What's the exponential form? Well, what would a be? 7 to the second equals x. B, 3 to the x equals y. Uh-oh, be careful with C. What's missing? The base, but it's a 10. So 10 to the second equals y. And same thing with D, it'll be e to the fourth equals c. Got it? Easy. Okay. Example 3, now you're gonna evaluate without a calculator, okay? So everyone in the world knows you can type this in on your calculator, but we're not gonna do that. We're gonna find the log base 2 of 8. Okay? So, why don't you, on erasing my board here, why don't you see how many of those you can figure out in example 3? And then we'll talk about the ones you can't get figured out. Are we coming? Are we getting some answers?
Yeah.
Think we got them all, Fred? Just in case somebody's not sure what's going on, let's do the first one together, and then we'll just give answers for the other ones and take questions if we've got them. So let's look at, this first one says log base 2 of 8. There are 2 ways, at least 2, that you can approach this problem. What I like to do is set it equal to x and then move through it. So 2 to the what is 8? And so I know the answer is 3, okay? Now another way, and this is kind of an important property we should talk about, is we all know that 8 is 2 cubed. So the problem is really find the log base 2 of 2 cubed. And when the base of the logarithm and the base of the exponent are the same, since they're inverses, they cancel each other out, and the answer is just 3. So you can do it that way too. So if you have the log base x of x to the y, the answer will always be y. Okay? So, any question about that? Everybody good?
Can we just do H? I think I got it.
We haven't got any answers yet.
Oh,
Let's get
alright.
the answers and see. All right, so what do we get for B? 2. C, 5. D, 2, because there's a base of 10 in there, right? E, 1/2, because 16 to the 1/2 is 4. Ooh, F, 0. Because if we say log base 3 of 1 equals something, that means 3 to the something has to be 1. And the only power you can raise 3 to and get 1 is the 0. Would it matter in the problem if this had been a 4? No. In fact, the log of 1 is always going to be 0, right? No matter what the base is. And that goes back to your BFF. Do you remember your logarithmic curve? What point did it always go through? 1, 0. If you plug in 1, you're going to get 0 every time. All right, how about G? 1. And how about H?
-2.
What did you say?
-2.
-2. -2. Because 36 is 1 over 6 squared. And 1 over means negative exponent, so 6 to the -2nd. All right, let's type these in on our calculator. All right, you guys with the new calculators, you have a bit of an advantage over us with the older calculators. Log 9, easy, press log 9, right? Where do we get when we press log 9? 0.954.
Yeah.
4 places after the decimal, so 0.9542. Right? Log 6125. 3.7871. These are just type in. Now, be careful with C. On my calculator, one of the old ones, I just can't type log 10 because why? The base is 2. And if I'm pressing my log button, my button that says LOG, then the base is automatically 10. If it has a different base, then I gotta be careful. So if you have a calculator like mine, I want you to think about this for a second. We are being asked to evaluate this, and that means that 2 to the x equals 10, right? So now I'm going to take the logarithm of both sides, because that will pull my exponent off in front. And what I end up typing in on my calculator is log 10 over log 2. Now, this is a little ahead of some of the stuff we talked about, but you did this last year. So this is what I ultimately ended up typing in on my calculator. Let's look at the original problem. I wonder if I could have gone straight from here to here. Yes, because this is the change of base formula, and it says automatically the answer to this question is going to be the log of, I call this the top number and this the bottom number. So it's going to be the log of the top number over the log of 2. You don't have to go through all this. That will happen every time. Now, when you type that in, be very careful that you're closing the parentheses before you hit divided. So log 10, where am I? Log 10 divided by log 2. 3.3219, right? Now you guys are the newer calculator. You have a distinct advantage because you have a button that tells you to fill in the boxes, so you can fill in your own base and your own number and just go directly to the answer. I don't know, where is that button?
Math A.
It's math and
It's
then
in
just
the math menu,
press math.
one of the options.
We also have math.
I don't.
Oh, you don't?
I think mine is so old, I don't. So I know some of the fat ones do, but mine doesn't. Okay? All right, it's good to kind of know the math anyway, the logic behind it. And that's what that is right here. So we got one more of those, right? So D is gonna be log, for me, it's gonna be log 135 divided by log 7. 2.5208. Okay. All right. One useful purpose for logarithms is when dealing with exponential data. Exponential data can be very challenging to display because the values start very small, but they grow quickly. We've observed that, right? Exponential growth. So somebody has taken the data of English Americans in the United States in 1620, and they graphed it. And look at that first graph. That is a very classic exponential graph. Would you agree? But it's a little bit problematic because literally the first half of the graph, it's very hard to read it. Because if I said to you, how many people were there at the 20th year, and then at the 30th year, and at the 40th year, you really can't tell. Because they had to scale everything from 0 to 7 million. So all those first values are all crunched up down there at the bottom. You see what I'm saying? So it's really hard to interpret it, other than it's growing fast. Okay, so look at the one next to it. Those are the same data points, the exact same data points, but the y's are logarithmically scaled. This is called a semi-log plot. And we are now plotting the exact same set of points, but on a logarithmic scale, which means powers of 10. Okay? So, apparently, at the 40th year, it was somewhere between, what, 10,000 and 100,000? Or is that right? 10 to the 4th, 10,000 and 100,000? And then at the 60th year, it was closer to 100,000. So the data is easier to interpret when you look, for this particular data, it's the first half of it, it's easier to interpret in that kind of plot. All right, let's look at example 5. Can you plot the data points? T is the years since 1620. So the years since 1620. So 1840 would be what? 220? Can you plot 17 million on your graph? Where is 17 million going to be? Well, what's 1 million? 10 to the 6th? 6? Yeah, 10 to the 6th. 1,000 is 3, 10,000, 100,000, no, 10 to the 6th. And then, what's 10 to the 7th? 10 million. So if we want 17 million, we need to be more than 10 to the 7th, don't we? What's 10 to the 8th? 100 million? So we're above 10 to the 7th, close to 10 to the 7th. A lot closer to 10 to the 7th than 10 to the 8th. All right, do the same thing with 31 million and 50 million. Go ahead and plot those points. They're all gonna be between what? 10 million and, or 10 to the 7th and 10 to the 8th. Yep.
Actually, never mind. Just correct myself. When these numbers get so big, and like, it's 10 to the 7th and 10 to the 8th is like, it's gigantic. Are they gonna end up looking like they're all on the same line?
They're going to look leveled out. They're not gonna be on the same line. They're gonna be getting bigger, but yeah, you're not gonna see the gigantic jump that you would see if you did it exponentially. See, when you do it exponentially, look at that. Look at it shooting up. When you do it logarithmically, they are still increasing. That is an increasing curve, but you're not seeing the dramatic increase. And it's all a matter of scaling it. It's a scale. All right, one common type of graph with a logarithmically scaled vertical axis includes grid lines as seen below. This is likely, and it did, appear on the AP Pre-Calculus exam. Okay, so we have to be able to use this data. So, keep in mind, okay, let's look at the y-axis, okay? See the 10 mark on the y-axis? The line right above that, okay, so that's 10 to the first. 100 is 10 to the second. What are all those lines in between? 20, 30, 40, 50, 60, 70, 80, 90, and then we get to 100? And then what's after 100? 200, 300, 4, 5, 6, 7, 8, till we get to 1,000? Everybody clear on that? All right, go ahead and plot your points then. With that in mind, plot your points. $20 is the first horizontal line above the 10. Okay? Good. Points look like these. You're not even on the right page.
I just flipped it. Flipped the wrong way.
Points look like these. Points look like this.
There's a bigger gap between 10 and 11 than there is 11 and 12.
That's not 10 and 11. That's
Oh, I know,
20.
I know. But
This round was just
it's gonna be a little more than halfway.
Yeah. Yeah, you have to approximate that one.
It's a little above the middle.
Yeah, you gotta approximate it, but yeah. Okay, we got it? Bennett? Got it? Okay, all right. So 2/9 is gonna be due on, Tuesday. All right, 2/9 is gonna be due on Tuesday, and we are moving on to
10 to
2/10.
100. 10 is what I don't get. Yeah. So like, it'll be like, if this was 10, and this was 20 right here, it'd be like
You have another
11,
homework packet.
12,
It might be,
13.
I mean, I had to divide it, too many to put in one packet, so I made 2 packets and maybe those two. So you have it.
It's hard to explain, but like,
I don't know, is it the
That's
first
fine, yeah.
page of the new
you
packet?
see how the gap between 10 and 20 is a lot
All
smaller
right.
between, or a lot bigger than.
Does someone
10
have
or
2/9?
20.
I just want to validate, yeah.
Yeah.
All right. 2/10, here we go, notes for 2/10.
It's like so.
General form of a logarithmic function, all right, there it is, a log base b of x, okay. Exponential functions and logarithmic functions are inverses of each other. Okay. All right. So for exponential functions, over equal width input value intervals, the output values change multiplicatively. So look what right there where it says recall, right underneath, see that chart? Where the x's are going 1, 3, 5, 7. and the y's are going 2, 4, 8, 16, you would say to me, I hope at this point, that is exponential. Right? We're all good with that. If I do the inverse, then remember what an inverse does. If I do the inverse, then I would have the next little chart there, where the x's are 2, 4, 8, 16, and the y's are 1, 3, 5, 7. That is the characteristic of a logarithmic function. So, how do we know something is exponential? Equal input, or equal with inputs, and outputs are being multiplied by something. Logarithm is exactly the opposite. The inputs are being multiplied by something. So the inputs are geometric, but the outputs are arithmetic. They're going up by an addition or subtraction. Okay, so with that in mind, example 1. See what you can figure out with your, are they logarithmic, exponential, or neither? Those are your 2 or 3 options. Logarithmic, exponential, or neither.
Wait, what is it when they're both been multiplied?
Remember, your options are logarithmic, exponential, or neither. You guys done? All right, let's talk about it.
Exponential, logarithmic,
What did you think about number 1?
exponential.
Exponential. Because why? If you had to explain that, what would you say?
The x's are being added and the y's are being multiplied.
So the
Inputs.
x's are equal with inputs, right? They're going up by the same amount, adding. And then the y's are proportional. They are being multiplied by the same number. Okay, good. What about B?
Logarithmic.
Logarithmic, because it's the exact opposite. Perfect. Okay. What about C?
Neither.
Neither, because both sides are going up geometrically. Right? So that's neither. Not to say it's not some function, we couldn't graph it, but it's not exponential and it's not logarithm. All right, what about D?
Logarithmic.
Logarithmic. Because your x's are being times by 2 and your y's are being subtracted by 3. Perfect. All right, 2 important properties of inverse functions. Graphs of inverse functions are reflections of each other over the line y equals x. Let's look at that for just a second. I graphed my logarithm a second ago. And remember, my logarithmic function looked like this. Right? Now, tell me about my exponential. What does my exponential look like? It has an asymptote here. So in other words, instead of x equals 0, its asymptote is y equals 0. It contains the point 0, 1. It looks like that. Are those reflections of each other across the identity line? They absolutely are. They are inverses of each other. Okay, and then the other important point is, if I have a point on my logarithm curve, then the flipped point would be on my exponential curve. Right? Okay. Example 2. Show that f and g are inverse functions. Now you had to do this in your homework. Some of you did it well, some of you did it not so well. If things are inverses, then f of g of x equals x, and g of f of x equals x. That needs to be written down on the paper, okay? That's how you show things are inverses. All right, well, let's see if this is true. Right now, I don't know that that's true. We haven't done the problem yet. So, f of, this is f of g of x, means plug g into f. So that would look like, let's see if I put g in f, that would look like 3 to the log base 3 of x. Would you agree with that? And a second ago, problem didn't look exactly like this, but a second ago I told you that when the base of the exponent and the base of the logarithm are the same, they cancel, and this just indeed does equal x. So the property probably is going to happen in this way, but the property is like twofold. It says log base b of b to the x will always be x. When these two numbers match, right here, this is the base of the log, this is the base of the exponent. When those match, it's just x. That can look like this too. When the base of the exponent and the base of the logarithm match, it's just x. Those are properties of logarithms. Alright, so let's see what the second one says. G of f. So that means plug f into g. So that's gonna be log base 3 of 3 to the x. Well, we just talked about it. These two match. So the answer is x. They are indeed inverses of each other. All right, go ahead, example 3, go ahead and sketch your logarithmic function. Log base 2, which will simply be the flip-flop of the one he drew to the x. So flip-flop some ordered pairs, and your picture should look something like this one right here. Did you get a picture that looked like this black one? By flipping the ordered pairs? Or folding across the identity? You good? Alright, one more thing to do here. And then we'll do some check your understanding. Let's look at example 4. The exponential function contains the point 2, 3. So this is your exponential. We got the point 2, 3, and 627. All right. So y equals log base a of x will be the inverse of this. So what will his ordered pairs be? 3, 2, and 27, 6. You're gonna find the average rate of change, oh my gosh, right out of 1.1, going all the way back to day 1 almost. How do we find an average rate of change?
Rising for y slope.
We're going to take,
27 minus 3.
this is gonna be the inverse, I'm gonna have to give it a name. So we're gonna take h inverse of 27 minus h inverse of 3 and divide that by 27 minus 3. This is H inverse right here, so what's H inverse of 27? 6. H inverse of 3 is 2 divided by 24. So your average rate of change is 1/6. And if we had any context, we put a label on that, like feet per minute, or gallons per hour, or something like that, right? But we don't, so. All right, check your understanding. You and your partner, let's take 6 minutes, get as much of it done as you can together, and then we'll check what you have done.
Somebody wanna come back here? Yeah, behind the back there.
By the way, I got to hold little Savannah last night. She's
How many pounds?
She was only, well, she is 7 and a half. 7, 8, I think, yeah, that'd be 7 and a half.
Okay.
So she was fine size.
So for E, it's
My
log
baby's
E.
was, like, my last one was 9 and a half.
Oh, wow,
Yeah,
that's
so
big.
I
LM
used
means
to
log
look
E.
bigger, bigger.
Cancel the E, so it's 3. Mark for.
All right, Owen's flying through number 1. Let's see if we can get some more done on the page.
So look, ln means log E, right? Yeah, and then it's E to the 3. So that big E to the 3. There's another E right there. So it's just log ln equals log E. Yeah, so it's log E to the E to the 3rd. So another E right there. To the 3rd. Because log E, this log E equals ln. So that's that. And then when the base and the base of the exponent are the same, you cancel them out. So it's just 3.
When the base and the thing are equal, then you just take the top number, or you take the exponent. Right? Yeah. Because when these are.
That is a property of logarithms. They're inverses of each other, so they cancel. All right. Let's run down through the answers for number 1. A was,
5.
B was, C was 1/2. Everybody get 1/2? Because the square root of 36 is 6. How about D? What'd you get for that one? -2, very good. Anytime you see 1 over, you're gonna think about a negative, because that's how you get 1 over. And how about E? 3, because ln, remember, is log base E. So log base E of E cubed is just gonna be 3. And with my other classes, we just have a blanket rule, and it's true, it works. I'm giving it to you too. When an ln and an E are in direct contact with each other, so there's no radical in between them, or there's no number in between them, if it's ln E, they're always gonna cancel, because of the fact E is the base of the logarithm, and E is the base of whatever's coming after it, so they always cancel. So the minute you see ln E, whoop, gone, answer is 3. All right, did you complete the tables?
Yep.
Now, they got a little tricky because you got started and you were just flipping them, right? But what happened with 81? Yeah, that was not, that point didn't match up, so 81 is 4, right? Because 3 to 4 is 81. So if you got carried away and you just started flipping, the last ordered pair in the top chart is 327. The last ordered pair in the bottom chart is 81.4. What's the relationship between F and G?
They're inverses.
Obviously, they are inverses. You can look at the chart, the numbers that happened in the chart, they're flip-flops of each other. D would be a proof, finding the composition. We just did that a minute ago with a different base, but they're going to be inverses of each other. And C, for the top one, as the inputs grow additively, the outputs grow multiplicatively. That is an exponential function. The bottom one, as the inputs grow multiplicatively, the outputs grow additively. That is a logarithmic function. Okay? 2.8 or 2.9. 2.9 is due Tuesday. 2.10 is due Wednesday.
Do we have 2.9?
Yes, we talked about that already. I gave you 2 when I handed out all the stuff. I gave you 2 homework packets because I couldn't staple it all together. So I handed it all out at the beginning.
Oh, yeah. Far back on the
Look at little.
Right there it is, yeah.
Is there like a final that you guys? I don't.
Not yet, there's not.
You big red one?
Where's the other one?
The flavor, what's it called?
What?
The one you're obsessed with?
I like the blue ones. Yeah, blueberry and cherry go crazy.
True berry.
Yeah.